1 light-year. The distance that light, travelling at 299,792,458 meters per second, the fastest that anything in the universe can move, the hard physical limit that Einstein's special relativity places on the propagation of information through space, covers in 1 year. 1 year of continuous travel at that incomprehensible speed. The distance that results is approximately 9.46 trillion kilometers. 9.46 followed by 12 zeros. A number that, written out in full, is 9,460 billion kilometers. This is not the distance to the nearest star. The nearest star system, Alpha Centauri, the triple system that includes Proxima Centauri as the closest individual stellar body to our Sun, is approximately 4.24 light-years away. 1 light-year is not even a quarter of the way to our nearest stellar neighbour. 1 light-year would take us from the Sun to a point in interstellar space between stars in the dark void between our solar system and the closest other one. An empty point in the galaxy, surrounded by nothing of significance, not yet arrived at anything worth arriving at. And the question we are going to examine tonight is how long it would take humanity, with the technology we actually have, and with the technology we might plausibly develop, and with the technology that physics permits but that we cannot yet build, to cross just that 1 light-year. Not to reach Alpha Centauri, not to explore the galaxy, just to cross the first unit of the interstellar scale. 1 light-year. 9.46 trillion kilometers. The answer, across different technological epochs, tells us something about where we are in the cosmos and what our actual relationship to it is. Not what we imagine it to be in science fiction, not what the inspiring speeches about humanity's destiny among the stars suggest. What it actually is, right now, with what we have, and what it might be in futures that are realistic rather than fictional. Before we begin, if you're here because the night is long and you need something to settle into, stay with this. The distances involved are real. The times involved are real. And sitting with both of them honestly is worth doing. Let us start at the beginning, with what we actually have, with the technology humanity has already demonstrated and deployed in the real world, not in proposals or simulations, but in actual functioning hardware that has actually travelled in space. The fastest human-made object ever launched from Earth is the Helios 2 solar probe, a joint German-American mission launched in 1976 that achieved a maximum speed of approximately 70.2 kilometers per second at its closest approach to the Sun. This speed was not produced by any conventional propulsion system in the continuous sense. It was produced by the gravitational slingshot effect. The spacecraft approached the Sun in a carefully calculated trajectory that converted the Sun's gravitational potential energy into kinetic energy, accelerating the probe to a speed that no rocket engine at the time could have produced directly. 70.2 kilometers per second. This is faster than any spacecraft has travelled before or since in terms of instantaneous velocity relative to the Sun. At this speed, Helios 2 was covering approximately 252,000 kilometers per hour, roughly 330 times faster than a commercial airliner. It sounds fast. It is fast. By any human standard, it is extraordinarily fast. At 70.2 kilometers per second, crossing 1 light-year would take approximately 4,271 years. 4,271 years. To put this in historical context, 4,271 years ago, humanity was in the early Bronze Age. The pyramids of Giza were being constructed. Writing had existed for only a few centuries. The entire recorded history of Western civilization, from ancient Mesopotamia to the present day, spans approximately 5,000 years. With our fastest ever spacecraft, crossing 1 light-year would take nearly the entirety of recorded human history. But Helios 2's speed was achieved at closest solar approach. The spacecraft was decelerating immediately after and would not maintain that speed. A spacecraft heading for interstellar space would not benefit from solar gravity in the same way and would be limited to the exhaust velocity of its propulsion system and any gravitational assists it could obtain from the planets it passed. The Voyager probes provide a more realistic baseline for interstellar travel with current technology. Voyager 1, the most distant human-made object in existence, is currently travelling at approximately 17 kilometers per second relative to the Sun. This speed was achieved through a combination of its launch velocity and gravitational assists from Jupiter and Saturn. At this speed, Voyager 1 would take approximately 17,500 years to cross 1 light-year. 17,500 years. Modern, anatomically identical humans have existed for approximately 300,000 years. 17,500 years ago, the last ice age was ending. Humans were crossing land bridges between continents. Agriculture had not yet been invented. The entire history of human civilization, from the first cities to the present moment, would fit approximately 3.5 times into the travel time required to cross 1 light-year at Voyager's speed. Voyager 1 is not headed toward any star in particular. It is heading in the direction of the constellation Ophiuchus. Even if it were aimed directly at the nearest star, it would not arrive for approximately 73,000 years, and it will long since have exhausted its power supply and gone silent before any such crossing could occur. These numbers are the actual state of human interstellar capability, not pessimistic estimates, not worst-case scenarios, the actual performance of the actual fastest hardware humanity has ever built and launched. 1 light-year takes somewhere between 4,000 and 17,000 years with the technology we have deployed. Let us now examine whether nearer-term proposed technologies, systems that are being seriously studied or developed, rather than merely imagined, could substantially improve on this. Chemical rockets, the technology that has launched everything humanity has ever put in space, from the first Sputnik to the current Starship, are fundamentally limited by the specific impulse of their propellants. Specific impulse is a measure of fuel efficiency. It tells you how much thrust you get per unit of propellant consumed. The best chemical propellants, liquid hydrogen and liquid oxygen, achieve specific impulses of approximately 450 seconds. This translates to exhaust velocities of approximately 4.4 kilometers per second. The maximum speed a rocket can achieve is limited by the Tsiolkovsky rocket equation, the relationship between the exhaust velocity of the propellant, the ratio of initial to final mass, and the resulting change in velocity. For chemical rockets, the math is unforgiving. To achieve 17 kilometers per second, Voyager's current speed, with a hydrogen-oxygen rocket, requires a mass ratio of approximately 47 to 1. The rocket must be 47 times heavier at launch than it is at final velocity. To achieve 100 kilometers per second requires a mass ratio of approximately 1.6 times 10 to the 9th. The rocket must be 1.6 billion times heavier at launch than at arrival. This is obviously not physically achievable. Chemical rockets cannot, under any circumstances, achieve the velocities needed to make interstellar travel feasible on human timescales. The fundamental chemistry of propellants sets a ceiling on exhaust velocity that no amount of engineering optimization can raise. The ceiling is too low. Chemical propulsion was never going to take humanity to the stars, and no amount of investment in chemical rocket technology will change this fundamental physical reality. Nuclear thermal propulsion, using a nuclear reactor to heat propellant and expel it at higher exhaust velocities than chemical reactions can achieve, offers a modest improvement. The NERVA program of the 1960s demonstrated nuclear thermal engines with specific impulses of approximately 800 seconds, roughly twice the best chemical systems. This translates to exhaust velocities of approximately 8 kilometers per second. Better than chemical rockets, still insufficient for interstellar travel. A nuclear thermal rocket heading for a light-year crossing would take roughly 30,000 to 40,000 years. Nuclear pulse propulsion is the first technology that begins to make a meaningful dent in the interstellar timescale. The Orion concept, developed at General Atomics in the late 1950s and studied seriously by some of the most talented physicists of the era, including Freeman Dyson, proposes using a series of nuclear explosions behind a spacecraft to propel it to high velocities. Small nuclear bombs, or nuclear pulse units as the engineers preferred to call them, would be detonated at a rate of approximately 1 per second behind a massive steel pusher plate. The explosions would accelerate the plate would compress shock absorbers, and the ship would be propelled forward at velocities far exceeding what any conventional rocket could achieve. Detailed engineering studies of Orion suggested that an interplanetary version of the spacecraft could achieve velocities of approximately 100 kilometers per second using fission pulse units. A more advanced interstellar version using thermonuclear fusion pulse units could in principle achieve velocities of approximately 10,000 kilometers per second, about 3% of the speed of light. At 3% of the speed of light, crossing 1 light year would take approximately 33 years. 33 years. This is a number that begins to make the crossing feel at least conceptually possible for a human mission. A journey that falls within a human lifetime, even if barely. A crew launched young might arrive old but alive. A multi-generational mission with this technology would not require more than 1 or 2 generations to complete the crossing. But Orion was never built. The 1963 Partial Nuclear Test Ban Treaty effectively ended the program by prohibiting nuclear explosions in space. The technical challenges were enormous. The pusher plate must survive being hit by repeated nuclear explosions while remaining structurally intact and transferring the impulse efficiently to the crew. The engineering solutions proposed were plausible but not tested. The political environment of the early 1960s nuclear age was not hospitable to the idea of a spacecraft that functioned by setting off nuclear bombs in near-Earth space. The modern descendant of Orion thinking is Project Daedalus, a detailed engineering study conducted by the British Interplanetary Society in the 1970s and subsequently updated as Project Icarus. Daedalus proposed using inertial confinement fusion, small pellets of deuterium and helium-3 ignited by electron beams or lasers as the energy source for a pulse propulsion system. The design aimed at achieving approximately 12% of the speed of light, fast enough to reach Barnard's star in approximately 50 years with a one-way unmanned probe. At 12% of light speed, crossing 1 light year would take approximately 8 years. 8 years. a number that begins to feel genuinely accessible on human timescales, faster than many historical sea voyages, shorter than many geological and archaeological research programs. The problems with Daedalus are substantial. Helium-3, the primary fuel, is extremely scarce on Earth and would need to be mined from the atmospheres of the gas giant planets, most likely Jupiter or Uranus. The quantities needed are enormous. The Daedalus design called for approximately 50,000 tons of helium-3 and 100,000 tons of deuterium. The fusion ignition technology required, reliably igniting tiny fusion pellets at a rate of 250 per second with extreme precision, is beyond current technological capability. Controlled nuclear fusion itself has not yet been achieved in a sustained net energy-producing form, even in large laboratory facilities. Scaling fusion down to the pellet ignition approach required for Daedalus involves additional technical challenges that have not been solved. Project Daedalus represents serious engineering, not science fiction, but a real engineering study conducted by real engineers applying real physics. But its realization would require technological advances on multiple fronts simultaneously, each of which represents a substantial research and development challenge. The specific target of helium-3 mining from gas giants alone would require a space infrastructure far beyond anything currently planned or funded. The laser sail concept, the approach most seriously pursued today for near-term interstellar probe development, takes a fundamentally different approach to the propulsion problem. Rather than carrying its energy source, the spacecraft is pushed by a beam of laser light from a large installation at its origin point. The spacecraft carries a lightweight, reflective sail, perhaps a few meters to a few hundred meters in diameter, that reflects the laser beam and receives momentum from the reflected photons. The spacecraft itself carries no propellant and no power source for propulsion, making it potentially extremely lightweight. The Breakthrough Starshot initiative, announced in 2016 and backed by significant private funding, including from Yuri Milner, proposes accelerating gram-scale spacecraft, essentially chips with sails, to approximately 20% of the speed of light using a laser array with a combined power of approximately 100 gigawatts. At 20% of light speed, crossing 1 light-year would take 5 years. The spacecraft would reach Alpha Centauri in approximately 20 years and could transmit data back, at the speed of light, approximately 4 years after arrival, for a total time from launch to first data of approximately 24 years. This is the most credible near-term proposal for crossing interstellar distances on human-relevant timescales. The physics is sound, photon pressure is real and has been measured and used in various spacecraft applications. The engineering challenges are substantial but do not require new physics. They require laser arrays of unprecedented scale and power, manufacturing of reflective sails at unprecedented size and thinness, and systems for keeping the laser beam pointed at the sail with extreme precision over the 20-year acceleration phase. The cost and scale challenges are enormous. 100 gigawatts of coherent laser power is roughly equivalent to 10% of the total current global electrical power generation capacity directed into a single beam. Building the required laser array would cost estimates range from several billion to tens of billions of dollars, depending on assumptions about technology maturation. The sail material must be reflective enough to avoid being vaporized by the laser, thin enough to minimize mass, and large enough to capture sufficient laser power for adequate acceleration. The specific materials capable of meeting all these requirements simultaneously may not yet exist. Even if all the engineering challenges are solved, Breakthrough Starshot, in its current conception, is a mission for tiny gram-scale probes, not for human crews. The mass ratios involved, the laser power required scales with spacecraft mass, make the approach economically prohibitive for anything larger than a very small unmanned probe for the foreseeable future. A gram of spacecraft mass can be accelerated to 20% of light speed with approximately 100 gigawatt-hours of laser energy. A human crew with minimal life support might mass several tons, a factor of 1 billion more than a gram. The laser energy required scales proportionally and becomes completely impractical. For crossing 1 light-year with a human crew, none of the proposed near-term technologies is adequate. Chemical rockets require tens of thousands of years. Nuclear thermal propulsion requires tens of thousands of years. Nuclear pulse propulsion using fission might bring it down to thousands of years, still not human-crewed viable. Fusion pulse propulsion at Daedalus scale might get the crossing time to decades, but requires fusion technology that does not yet exist and fuel resources that are not accessible. Laser sails at breakthrough Starshot power levels could cross 1 light-year in 5 years, but cannot carry human passengers with any near-term laser array. The honest answer for human crew crossing of 1 light-year with technology achievable in the next century is that it remains an enormous challenge. Not impossible, physics does not forbid it, but requiring either technologies that do not yet exist or mission architectures, generation ships, human hibernation, but raise their own profound challenges. Let us now talk about the concepts that go beyond near-term proposals into the realm of what physics permits, even if we cannot yet build them. The technologies that would require decades to centuries of scientific and engineering development, but that do not violate the laws of physics as we currently understand them. The most discussed, physically plausible advanced propulsion concept is antimatter propulsion. Antimatter is the mirror image of ordinary matter. Every particle has a corresponding antiparticle with the same mass but opposite charge and other quantum numbers. When a particle meets its antiparticle, they annihilate completely, converting their combined mass into energy according to Einstein's E equals mc squared, with 100% efficiency. This is the most energetically efficient reaction that physics permits, far more efficient than nuclear fission, which converts approximately 0.1% of mass to energy, or nuclear fusion, which converts approximately 0.7%. Antimatter annihilation converts 100% of the annihilated mass into energy. If you annihilate 1 kilogram of matter with 1 kilogram of antimatter, the result is 1.8 times 10 to the 17 joules of energy, approximately equal to the energy released by 43 megatons of TNT, or roughly 3 times the yield of the largest nuclear weapon ever detonated, from 2 kilograms of fuel. This energy density makes antimatter the theoretically ideal rocket propellant. An antimatter rocket using electron-positron annihilation, the simplest form, would produce gamma rays rather than a directed exhaust stream, which creates engineering challenges because gamma rays cannot easily be reflected and are intensely ionizing. More practical designs use antiproton-proton annihilation, which produces pions, charged and neutral particles, with the charged pions having some momentum that can contribute to thrust, and the neutral pions decaying to gamma rays. Various schemes for directing the charged pion exhaust to produce thrust have been proposed. The exhaust velocity achievable with antimatter propulsion depends on the specific design. But theoretical calculations suggest exhaust velocities approaching the speed of light are, in principle, achievable. With exhaust velocities close to the speed of light, the Tsiolkovsky equation allows meaningful final velocities with realistic mass ratios. An antimatter rocket with a mass ratio of approximately 4:1, 4 times as much mass at departure as at arrival, could in principle achieve a final velocity of approximately 40% of the speed of light. At 40% of light speed, crossing 1 light year would take approximately 2.5 years. A mission to Alpha Centauri at 40% of light speed would take approximately 10 years one way, within the range of what a crew could endure without multi-generational succession. The problem is the antimatter. Producing antiparticles requires enormous energy and is extraordinarily inefficient with current technology. The world's most powerful particle accelerators, the Large Hadron Collider at CERN, produce antiprotons as a byproduct of high-energy proton collisions. But the production rate is measured in nanograms per year at best. The energy cost of producing antimatter through particle acceleration is roughly 1 billion to 1 trillion times the energy that annihilating the antimatter would release. The process is not even remotely energetically favorable with current technology. Storing antimatter is equally challenging. Antimatter must be stored in vacuum containers isolated from contact with ordinary matter using magnetic trapping, penning traps for charged antiparticles. Current penning traps can hold perhaps a few micrograms of antiparticles for periods of minutes to hours. Scaling this technology to store the kilograms to tons of antimatter needed for an interstellar mission represents an improvement in capability by a factor of roughly 10 to the 15th to 10 to the 18th, 15 to 18 orders of magnitude. The technological gap between current antimatter storage and interstellar antimatter rocketry is as large as the gap between a single transistor and a modern processor with billions of transistors, enormous but not obviously impossible on a centuries-long development timescale. The energy source for antimatter production is the other fundamental challenge. Producing enough antimatter for an interstellar mission requires energy inputs measured in zettajoules, 10 to the 21 joules. Current global annual energy production is approximately 5 times 10 to the 20 joules. Producing the antimatter for a single interstellar mission at current energy costs would require several years of total global energy production, and at current production efficiency would waste essentially all of that energy as heat. Either dramatically more efficient antimatter production methods must be developed, or global energy production must be scaled up by orders of magnitude before antimatter propulsion becomes economically feasible. These challenges are not small. They represent fundamental technological barriers that cannot be overcome by incremental improvement of current technology. They require qualitative breakthroughs in antimatter production, storage, and energy generation that are not foreseeable on any specific timeline. But they do not violate physics. Antimatter propulsion at the level needed for interstellar travel is not physically impossible. It is technologically remote, centuries rather than decades away, but within the space of what physics permits. Let us now talk about the concept that most directly confronts the time problem of interstellar travel. Not by going faster, but by changing the relationship between the traveller and time. This is not science fiction. It is a direct consequence of special relativity that is experimentally confirmed and mathematically precise. Special relativity tells us that time passes differently for observers moving at different velocities. A clock moving at high velocity relative to a stationary observer runs slow. It ticks fewer times per second as measured by the stationary observer. This is called time dilation, and it has been confirmed to extraordinary precision by experiments with atomic clocks on airplanes, by measurements of cosmic ray muons that survive to reach Earth's surface only because their internal clocks are running slow at relativistic speeds, and by precise GPS timing systems that must account for both special and general relativistic time dilation to function correctly. The time dilation formula from special relativity tells us exactly how much time dilation occurs at any given velocity. At 10% of light speed, the time dilation factor is approximately 1.005. Clocks on board the spacecraft run about 0.5% slow relative to clocks on Earth. Small, but real. At 50% of light speed, the time dilation factor is approximately 1.15. Clocks run about 15% slow. At 90% of light speed, the time dilation factor is approximately 2.3. Clocks run about half as fast as Earth clocks. At 99% of light speed, the factor is approximately 7. Clocks run about 7 times slower. At 99.9% of light speed, the factor is approximately 22. What this means for interstellar travel is extraordinary and counterintuitive. At 99.9% of light speed, a spacecraft crosses 1 light-year in approximately 1.0005 years of Earth time. The light-year still takes slightly over a year by Earth clocks because nothing can travel faster than light. But aboard the spacecraft, only approximately 0.045 years, about 17 days, would pass. The crew ages only 17 days while crossing 1 light year. At 99.999% of light speed, crossing 1 light year takes approximately 1.00001 years of Earth time, while only approximately 1.6 days pass aboard the spacecraft. At 99.9999% of light speed, the crew ages only about 4 hours, while Earth time elapses 1 year. This is not speculation, it is established physics. The equations of special relativity are among the most precisely tested in all of science. Relativistic time dilation is real and has been measured directly. At sufficient velocity, a human crew could cross 1 light year in any subjective time they desired, hours, days, weeks, while approximately 1 year plus travel time passes on Earth. The same principle extends to larger distances. A hypothetical spacecraft accelerating continuously at 1 g, Earth surface gravity, could cross the entire observable universe in approximately 45 years of shipboard time, while billions of years would pass on Earth. The problem is not the physics. The problem is the energy required to approach the speed of light closely enough for significant time dilation. The kinetic energy of a 1 kilogram object at 99.9% of light speed is approximately 31.6 times its rest mass energy, about 2.8 times 10 to the 18 joules. For a spacecraft of reasonable mass, say 100 metric tons including crew and life support, the kinetic energy at 99.9% of light speed would be approximately 2.8 times 10 to the 24 joules, roughly 5,000 times current global annual energy production. And this is the kinetic energy at final speed, not the total energy the spacecraft must process to reach that speed. A real spacecraft must carry its own propellant to reach this speed. unless it is externally accelerated by laser or some other mechanism, and the Tsiolkovsky equation applies with devastating consequences. To reach 99.9% of light speed with any realistic exhaust velocity requires mass ratios that make the rocket equation essentially impossible to satisfy. Even with antimatter propulsion at near-light exhaust velocity, the mass ratio needed to reach 99.9% of final velocity approaches 22, meaning the ship must be 22 times heavier at departure than at arrival. For a 100 metric ton crewed vehicle, this means 2,200 metric tons of antimatter fuel, which, as we have established, requires essentially unachievable production technology. The relativistic option for crossing 1 light-year in subjectively short times is therefore not a near-term technological option. It is a possibility that physics permits, but that would require energy and propulsion systems dramatically beyond anything achievable in the foreseeable future. The time dilation effect is real. Using it for interstellar travel in subjectively short times requires energy sources and propulsion technologies that do not exist. Let us talk about the generation ship concept, not as science fiction, but as a serious engineering and social proposal for interstellar travel that accepts the multi-decade or multi-century crossing times and addresses them through the continued existence and succession of human communities, rather than through speed. A generation ship is a spacecraft large enough and self-sufficient enough to house a viable human population for the duration of an interstellar crossing that may take many generations. The crew that arrives at the destination is the descendant, by many generations, of the crew that departed. The ship is not a vehicle for a mission, but a world, a complete ecosystem and social system that must function indefinitely without resupply or external communication. The minimum viable population for a generation ship is a subject of genuine scientific debate. Too small a founding population and genetic diversity collapses over generations. Inbreeding depression accumulates, deleterious recessive alleles become expressed. The population's ability to adapt to unexpected challenges declines. Population geneticists have studied the minimum viable population needed to maintain sufficient genetic diversity across a multi-century crossing, and estimates range from a few hundred to several thousand individuals, depending on assumptions about random mating, genetic bottlenecks, and the degree of genetic drift acceptable at arrival. A ship housing a population of several thousand people must be a world in the functional sense. It must produce food through agriculture or aquaculture or some combination of biological systems. It must process waste and recycle nutrients and water and air. It must have the social and institutional infrastructure to maintain social order, resolve conflicts, educate children, maintain technical competence, and sustain the mission purpose across generations of people who were born on the ship and have never known Earth and will never see the destination. The technical challenges of this are enormous. Closed ecological life support systems, systems that cycle all matter within the ship without external input, have never been built at a scale sufficient for a long-term human community. The Biosphere 2 experiment in the early 1990s, a large sealed ecological system in Arizona housing 8 people for 2 years, provided sobering lessons about the difficulty of maintaining a stable, closed ecosystem. The oxygen levels in Biosphere 2 dropped unexpectedly due to microbial activity in the soil consuming oxygen. Food production was insufficient and the crew lost significant weight. The experiment encountered numerous unforeseen technical and ecological challenges that required interventions, including breaking the sealed atmosphere on multiple occasions. Biosphere 2 was 8 people for 2 years. A generation ship must house thousands of people for centuries. The engineering challenges scale in ways that make the Biosphere 2 lessons look straightforward. Every aspect of the ecological system must be redundant. Failure of any critical component cannot be allowed to cascade to mission failure. The genetic diversity of the plant, animal and microbial populations supporting the ecosystem must be maintained. The agricultural systems must produce sufficient calories and micronutrients indefinitely. The water and air recycling systems must function without fail for timescales measured in centuries. The social and governance challenges are equally daunting. A generation ship community must solve all the same governance problems as any human community: how to resolve disputes, allocate resources, manage individual rights against collective needs, respond to demographic and social change, but without any of the escape valves available to terrestrial communities. On Earth, a dissatisfied minority can migrate. A disagreeing faction can establish a competing community. An unsuccessful governance system can be reformed or replaced by external pressure or internal revolution in ways that allow the community as a whole to survive the political turmoil. On a generation ship, there is nowhere to go. Political conflict that cannot be resolved peacefully has no outlet except within the ship. A civil war on a generation ship is an existential threat to the entire mission. The psychological challenge of being born on a ship that you will never leave is genuinely novel. Every person born after departure will live their entire life in the same physical space, a space measured in kilometers at most, perhaps less. They will know from birth that they will never set foot on any planet, that they are transients in the universe in the most literal sense, passing between two worlds, belonging fully to neither. Their grandchildren may arrive at the destination world, but they themselves will live and die in transit. The question of what this does to human psychology, culture, and identity over multiple generations is genuinely unknown. Science fiction has explored these themes extensively, but science fiction exploration and scientific analysis are different. The actual human psychological and social consequences of generations of life in a closed system in interstellar transit cannot be determined from fiction. They require either actual experience of conditions approaching those of a generation ship, or theoretical modelling, drawing on the best available social and psychological science, or both. Neither has been done at the level of rigour that a mission plan would require. The governance structure of a generation ship is particularly challenging to design in advance, because the ship must be governed by the children and grandchildren and great-grandchildren of the people who chose to go, and those descendants did not choose to be on the ship. The founding generation can establish governance institutions and cultural norms and technical systems. They cannot guarantee that subsequent generations will maintain those institutions, observe those norms, or competently operate those systems. The gap between what the founders intended and what the ship actually looks like 3 or 5 or 10 generations into the crossing is a genuine unknown. Historical analogies are limited. Island populations maintained in isolation for many generations provide some evidence. The cultural and genetic evolution of isolated Pacific island populations has been studied in some depth and provides data on what happens to small, isolated human communities over generational timescales. The lessons are mixed. Some isolated populations maintained functional social systems and developed rich cultures appropriate to their environments. Others experienced catastrophic population collapse through internal conflict, ecological overexploitation, or demographic accident. The difference was often specific to the particular cultural inheritance and leadership of the founding population, factors that are difficult to engineer in advance. Religious communities and utopian communities of various historical eras provide another partial analogy. Groups of people who deliberately isolated themselves from the broader society to create specific kinds of human communities based on shared values. Some of these communities have been extraordinarily long-lived. Certain monastic communities have maintained continuous institutional existence for centuries. Others have collapsed within a generation of their founding. The lessons about what makes closed communities sustainable are real, but the application to a generationship is uncertain because the physical isolation of a generationship is absolute in a way that no terrestrial intentional community has ever experienced. Let us now talk about suspended animation, the concept of biologically pausing human metabolism during interstellar transit so that the crossing time passes without the crew aging or consuming resources. This is perhaps the most frequently imagined solution to the interstellar transit time problem in science fiction, and it is worth examining carefully because the distinction between what science fiction imagines and what biology permits is significant. True suspended animation, complete cessation of biological activity with reliable revival, has not been achieved for humans or for any mammal. The closest real-world analogue is the natural torpor of hibernating mammals, bears, ground squirrels, bats, in which metabolism slows dramatically but does not cease completely. Hibernating bears reduce their metabolic rate by approximately 75%, lower their core body temperature by several degrees, slow their heart rate to approximately 8 beats per minute, and maintain this state for several months. They do not freeze solid. Their metabolism continues at a reduced rate. They can be roused relatively quickly if disturbed. They emerge from hibernation without significant physiological damage. Induced hypothermia, reducing human body temperature to approximately 33 degrees Celsius for periods of hours, is used in cardiac surgery to reduce oxygen demand during procedures that temporarily stop the heart. Patients can survive hours at this temperature and recover without apparent neurological damage. Deeper hypothermia, temperatures approaching 10 to 20 degrees Celsius, has been used experimentally in emergency medicine for very short periods, and some patients have survived body temperatures as low as 13 degrees Celsius, with subsequent revival. The challenge for interstellar transit is the duration. Reducing temperature to suppress metabolism for hours or days is achievable with current medical technology. For months, the situation is much less certain. For years, it is essentially uncharted territory. The biological consequences of maintaining deep hypothermia for years, the effects on cellular maintenance and repair, on the immune system, on neurological function, on the integrity of DNA, are not well understood, and the practical challenges of preventing ice crystal formation in tissues at low temperature become more severe as the duration extends. Ice crystal formation is the fundamental physical challenge for deep cooling. At normal water-based biology, freezing produces ice crystals that puncture cell membranes and cause irreversible cell death. Cryoprotectants, chemicals that reduce ice crystal formation, can prevent this damage at moderately low temperatures, but become toxic at high concentrations, creating a balance between preventing ice damage and preventing chemical toxicity. Vitrification, replacing biological water with cryoprotectant solutions that form a glass-like amorphous solid rather than a crystalline ice, can in principle prevent ice damage entirely, but achieving complete vitrification of complex organs while maintaining viability has proved extremely challenging. Cryonics, the practice of cooling recently deceased humans to liquid nitrogen temperatures in the hope of eventual revival, applies vitrification techniques to the whole body. The goal is to preserve the structural information of the brain and body long enough for future technology to achieve revival. Whether this is achievable is scientifically contested. The relevant questions are whether the vitrification protocols currently used in cryonics preserve sufficient cellular and molecular detail for neural revival, and whether future technology could achieve the revival that current technology cannot. These are genuine empirical questions without current definitive answers. For interstellar transit, the goal is different from cryonics. Not preserving a deceased person, but maintaining a living person in a biologically arrested state, from which they can be reliably revived with no functional loss. This is harder than cryonic preservation in some ways. The person must be alive at both ends, rather than only at revival, and potentially easier in others. Complete vitrification to liquid nitrogen temperatures may not be necessary if shallower hypothermia can achieve sufficient metabolic suppression. NASA has funded research into induced hibernation for deep space missions, not for interstellar travel, but for the shorter transits within the solar system. The specific approach being studied involves cooling crew members to approximately 32 to 34 degrees Celsius for periods of weeks to months, through a combination of mild hypothermia and sedation. At this temperature, metabolic rate drops to approximately 50 to 70% of normal. Nutrient requirements decrease substantially, and the crew can be maintained in a small enclosed module rather than a full crewed habitat. Whether this approach can be extended to periods of years is uncertain. Whether it can achieve sufficiently deep metabolic suppression to be practically useful for multi-decade interstellar crossings is even more uncertain. A transit of 1 light-year at 20% of light speed, the breakthrough starshot laser sail concept, if scaled to crewed spacecraft, would take 5 years. Hibernation for 5 years at reduced metabolic rate would require nutrients and produce waste at rates that would still impose substantial life support requirements, would present genuine medical risks over the extended period, and would require reliable revival systems with no precedent at that duration. At 5% of light speed, more achievable with fusion propulsion technology, crossing 1 light-year takes 20 years. Hibernating for 20 years, with reliable revival at the end, is not within current medical capability, and its achievement would require fundamental advances in our understanding and control of human biology that cannot be timetabled. The honest assessment of suspended animation for interstellar travel is that it is a concept that biology does not rule out in principle. There are organisms that survive decades or centuries in dormant states, including certain tardigrades, bacterial spores, and plant seeds, but that achieving this capability for complex mammals, let alone humans, represents a gap in capability comparable to the gap between throwing a stone and achieving orbital velocity. Possible in principle, requiring developments that cannot be scheduled. Let us now talk about what lies beyond the physically plausible, but requires physics beyond our current understanding. The speculative propulsion concepts that appear in serious theoretical physics literature, but that have not been experimentally confirmed to work. Warp drive, the concept of compressing space-time in front of a spacecraft and expanding it behind, so that the spacecraft moves through space faster than light can travel through unmodified space, was formalized by Miguel Alcubierre in 1994 in a paper that took seriously Einstein's general relativity as the mathematical framework and derived a metric, a solution to the Einstein field equations, that describes such a space-time deformation. The Alcubierre metric is mathematically consistent with general relativity. It describes a region of space-time that would, if realized physically, allow apparent faster-than-light travel without violating the local speed of light limit for anything within the warp bubble. The problems are substantial. The Alcubierre metric requires exotic matter with negative energy density, to realize the space-time deformation. Negative energy density does not violate any fundamental principle of physics in isolation. The Casimir effect between closely spaced conducting plates produces a region of negative energy density between the plates. And quantum field theory permits localized negative energy densities under certain conditions. But the amount of negative energy required to create an Alcubierre warp bubble of spacecraft size is staggering. Early estimates suggested masses equivalent to the mass energy of a planet in negative exotic matter would be needed. Later theoretical work by Harold White and others has suggested that the required exotic matter mass could be substantially reduced by specific modifications to the bubble shape. Whether these modifications bring the required exotic energy within any achievable technological range is disputed. Most physicists who have analysed the Alcubierre metric and its variants conclude that the exotic matter requirements remain physically impractical regardless of these modifications. There are also fundamental questions about whether the warp drive concept is consistent with the full framework of quantum gravity, the as yet undeveloped theory that reconciles quantum mechanics with general relativity. In frameworks like string theory and loop quantum gravity, the specific spacetime geometries required for warp drives may not be realizable. Some analyses suggest that quantum effects within the warp bubble would destroy the bubble or the spacecraft within it. The causal structure of the Alcubierre metric creates paradoxes related to the fact that faster-than-light travel implies, in special relativity, the possibility of backward time travel, which creates self-consistency problems that no fully satisfying physical resolution has yet addressed. Warp drive, therefore, sits at the intersection of theoretically interesting and practically far beyond any current understanding of how to realize it. It is not definitively ruled out by physics as we understand it, but neither is there any physical mechanism by which exotic matter of the required type could be produced, or any indication that the quantum gravity problems can be resolved, or any experimental evidence for any aspect of the warp drive concept. Its status is best described as a mathematical curiosity that might or might not be realizable, depending on physics that we do not yet understand. Wormholes, shortcuts through space-time that connect distant regions by passing through higher dimensional space, are similarly interesting theoretically and similarly problematic practically. The mathematics of general relativity permits wormhole solutions. The Einstein-Rosen bridge is a mathematical description of a connection between two distant regions of spacetime. But traversable wormholes, ones that could actually be used by a spacecraft, again require exotic matter to hold them open. A wormhole without exotic matter would collapse almost immediately after forming. The quantities of exotic matter required are again enormous, and the theoretical and experimental status of traversable wormholes is no better than that of warp drives. The honest scientific assessment of both warp drives and traversable wormholes is that they are solutions to the equations of general relativity that require physical conditions that have not been observed, cannot currently be produced and may not be realizable by any technology. They are not definitively excluded by physics, but they are not supported by any physical evidence, and their realization would require either exotic physics beyond the standard model or resources and technologies that cannot be conceived in any near-term time frame. This brings us back to the honest accounting of where humanity actually stands with respect to crossing 1 light year. With current technology, chemical rockets, nuclear thermal propulsion, crossing 1 light year takes tens of thousands of years. With technology achievable in the next century or two, nuclear pulse propulsion, fusion propulsion, laser sails, crossing 1 light year takes decades to centuries, depending on the specific technology. With technology that physics permits, but that would require centuries to millennia of development, antimatter propulsion, extreme relativistic flight, crossing 1 light year could, in principle, be achieved in years or even days of shipboard time. With technology that may or may not be consistent with complete physics, warp drives, wormholes, the crossing time question becomes ill-defined because these technologies could, in principle, eliminate the crossing time problem entirely. Each of these categories requires honest characterization of what is established versus speculative, what is physically possible versus technologically remote, what is within the range of foreseeable development versus dependent on physics we do not yet understand. The interstellar distance problem is real. The solutions are at different stages of theoretical and practical development. None of them is close. All of them are being worked on in various ways by serious scientists and engineers. The question the distances force us to confront is not primarily technical, it is philosophical. It is the question of what our relationship to the universe actually is, not what we imagine it to be, not what science fiction has taught us to assume it is, but what the physics and the engineering and the biology actually say it is, given where we are in our technological development. We are very small. We are very slow. We are very young as a technological civilization. The universe is very large. 1 light year is not even a significant fraction of the distance to the nearest star, and crossing it, with the technology we actually have, would take longer than human civilization has existed. This is not a reason for despair. It is a reason for clarity. Understanding the actual scale of the challenge is the prerequisite for addressing it seriously, rather than addressing a cartoon version of it. The cartoon version, the one where interstellar travel is a matter of building a bigger, better rocket and pointing it at a star, is not what the physics says. The physics says it is harder than that, much harder. And understanding exactly how much harder, and in exactly what ways, is the beginning of thinking honestly about what it would take to change the situation. The crossing of 1 light year is the entry fee for genuine interstellar presence. It is not the destination. It is the threshold. And paying that entry fee is an engineering and scientific challenge of a scale that puts into perspective every other technological challenge humanity has ever faced. Let us talk about what the Fermi paradox means in the specific context of interstellar travel timescales, because the distances and the crossing times we have been discussing illuminate the paradox in a way that is more concrete and more troubling than the usual framing. The Fermi paradox is the observation that the universe is old, 13.8 billion years, and large, containing hundreds of billions of galaxies, each with hundreds of billions of stars, and that the conditions for the emergence of technological civilizations appear to exist in many places, yet we detect no evidence of any civilization other than our own. No radio signals, no megastructures, no modified stars. No evidence of any kind that intelligence has arisen anywhere in the observable universe, except on one unremarkable planet orbiting one unremarkable star in one unremarkable spiral galaxy. The interstellar travel timescale analysis makes the paradox more acute in a specific way. Consider that the Milky Way is approximately 100,000 light-years in diameter. At the speeds achievable with fusion propulsion, perhaps 10 to 20% of light speed, crossing the entire galaxy takes approximately 500,000 to 1,000,000 years. This is a long time in human terms, but it is less than 0.1% of the age of the galaxy. A civilization that arose 1 billion years ago, which is entirely possible given that sun-like stars existed 1 billion years ago, and that eventually developed fusion propulsion comparable to what we can theoretically design today, and that chose to expand through the galaxy, could have filled the entire galaxy with its presence on timescales that are short compared to the galaxy's age. Even at speeds much slower than fusion propulsion, even at 1% of light speed, achievable in principle with nuclear pulse propulsion, a civilization expanding through the galaxy by sending probes to the nearest stars, establishing outposts, and then sending further probes from those outposts to the next nearest stars, a relay approach, could fill the galaxy in approximately 10 million years. 10 million years sounds long. It is long in human terms, but the galaxy is 13.8 billion years old. 10 million years is 0.07% of the galaxy's age. If any civilization anywhere in the galaxy developed interstellar capability and chose to expand more than 10 million years ago, it could have been everywhere in the galaxy for essentially all of recorded human history. And we see nothing. No artifacts, no signals, no evidence of modification of stellar environments, no Dyson spheres, no gravitational lensing anomalies from megastructures, no anomalous infrared emission from stars surrounded by artificial constructions. Nothing. The interstellar travel timescale analysis therefore sharpens the Fermi paradox into a specific form. The question is not just why we see no signals from other civilizations. It is why we see no artifacts, why no civilization in the 13.8 billion year history of this galaxy has expanded to fill it in the way that physics permits and that the timescale analysis shows would be possible in a small fraction of the galaxy's lifetime. The possible resolutions cluster into familiar categories. Life may be rare enough that our civilization is the only one in the observable galaxy, or even in the observable universe. The great filter may be behind us. The difficult step from chemistry to complex technological civilization may be so improbable that it has occurred only once. Or the filter may be ahead. Civilizations may consistently fail to achieve the interstellar travel capability needed for galactic expansion, whether through self-destruction or through some systematic barrier to the development of advanced technology. Or civilizations may achieve interstellar capability but choose not to expand, for reasons that seem coherent to them but that we cannot predict from our current vantage point. Or our detection capabilities are simply insufficient to recognize the signs of expanded civilizations that exist around us in forms we do not recognize. What the interstellar travel timescale analysis adds to this familiar list is a specific constraint. The fact that our best physically achievable propulsion technologies require years to decades to cross 1 light year means that even for a civilization far more advanced than us, galactic expansion is a project measured in millions of years, not thousands. This means the absence of any evidence of expansion is more surprising than it would be if interstellar travel were easy. If the universe were more like science fiction, where ships can cross light years in days, the lack of evidence of advanced civilizations would be less surprising, because the project of expansion would require less time to complete. The actual physics makes the silence of the universe more difficult to explain, not less. Let us now talk about the specific psychological and philosophical implications of the crossing times we have calculated. About what it means for human beings to genuinely internalize the scale of the interstellar problem, rather than imagining it away. Most humans, most of the time, maintain a mental model of the universe that is scaled to human experience. The distances feel large but manageable. The moon is far, Mars is farther, the stars are very far, but the gradient feels smooth, as though it is just a matter of going further rather than of confronting a qualitative difference in scale. Science fiction reinforces this mental model by depicting interstellar travel as an extension of current modes of transportation. Faster ships, better engines, and you can go to the stars. The actual numbers destroy this mental model if you let them in. Voyager 1, travelling for 47 years, has covered less than 1,000th of a light year. 1 light year takes tens of thousands of years with current technology. The nearest star is more than 250,000 times the distance from Earth to the Moon. The Milky Way galaxy is 100,000 light-years across. At Voyager's speed, it would take 1.7 billion years to cross. The nearest large galaxy, Andromeda, is 2.5 million light-years away. These numbers do not scale to anything in human experience. The mental model of space as a very large version of the distances we are familiar with simply does not work at these scales. The universe is not big in the way that a country is bigger than a city. It is big in a qualitatively different way, in a way that makes every distinction in scale that matters in human experience completely irrelevant. The difference between 1 meter and 1 kilometer matters for walking. The difference between 1 kilometer and 10,000 kilometers matters for transportation. But at the scale of light years, the difference between 1 light year and 1,000 light years is less consequential than the difference between 1 meter and 1 millimeter is for particle physics. The scale is not just larger, but categorically different. Sitting with this difference, genuinely letting the numbers be as large as they are, rather than imagining them away, produces a kind of vertigo that the comfortable version of the space exploration conversation does not produce. The comfortable version says humanity is on its way to the stars, that it is a matter of developing the right technology, that future generations will travel between stars as casually as we travel between continents. The honest version says that even our most optimistic, physically achievable propulsion concepts require years to decades for a single light year, that the nearest star is 4.24 light-years away, that any trip there and back takes at minimum a decade, even in optimistic scenarios, and that the vast majority of interesting astronomical objects are thousands to millions of light-years away, distances that even the most advanced conceivable propulsion technology would require centuries to millennia to cross. This is not a counsel of despair. It is a counsel of accuracy. The universe is what it is. The physics is what it is. Our relationship to the cosmos is characterized not by our potential to traverse it, but by our position within it. Deeply embedded, unable to leave in any significant sense, separated from everything outside our solar system by distances that make the rest of the universe effectively unreachable on any human or civilizational timescale, with any technology we can currently envision. This reality changes what the universe means to us, not making it meaningless, but making it meaningful in a different way from the way the science fiction universe is meaningful. In science fiction, the universe is meaningful because it is a place to go, full of destinations, full of other civilizations, full of adventures that are accessible given sufficient will and technology. In the actual universe, it is meaningful because it is the context within which we exist, vast, cold, mostly empty, barely accessible even in principle, and for that reason, all the more extraordinary to be in. We are in the universe, all of it. The light from galaxies 13 billion light-years away arrives at our instruments continuously, and we read it with extraordinary precision and learn from it things about the structure of reality that change our understanding of our situation. We cannot go to those galaxies, not in any timescale that means anything, but we are not separated from them in the informational sense. The universe is transparent to light in ways that make everything in it visible to us, even if nothing in it is reachable by us. This is our actual relationship to the cosmos. Observers, not travelers, readers of a universe that we can see but not visit. Inhabitants of one small system, embedded in one small galaxy, surrounded by a universe that is both astonishingly open to our observation and astonishingly closed to our physical presence. Let us now talk about what this means for the long-term future of humanity, about what realistic scenarios for human expansion into the cosmos look like when they are based on the actual physics rather than on science fiction assumptions. The most realistic near-term expansion, the only genuinely near-term expansion, is within our own solar system. Mars, the Moon, the asteroid belt, the moons of the outer planets, these are accessible with current and near-term technology on timescales of years to decades. The challenges are enormous, but they are not fundamentally different in character from the challenges humanity has faced in other expansion efforts. The physics is not categorically different from Earth-based technology in the way that interstellar physics is. Within the solar system, humanity could, in principle, establish a genuinely spacefaring civilization, one with permanent human presence on multiple worlds, with industrial and economic activity spread across multiple locations, with the demographic and technological base to sustain complex technological civilization without dependence on a single planet. This is not easy. It is not cheap, but it is physically possible with technology that either exists or is foreseeable from current development trajectories. Beyond the solar system, the honest scenario for the next several centuries is robotic probes rather than human travelers. Breakthrough Starshot, or its successors, might send gram-scale probes to Alpha Centauri or other nearby star systems on timescales of decades from now. Machines that could transmit data from interstellar distances and begin the long process of characterizing what lies beyond our solar system through direct, in situ measurement rather than through telescopic observation alone. These probes would arrive at their destinations after 20 to 30 years of transit and would begin transmitting data that arrives another 4 years later, a process that extends beyond the planning horizon of any current institution, but that is physically achievable. Human interstellar travel on any timeline relevant to the next several centuries depends on technological developments that are not currently funded, not currently in development, and not achievable through incremental improvement of existing technology. Fusion propulsion requires achieving controlled nuclear fusion, a goal that has been pursued for 70 years and that remains frustratingly elusive. Antimatter propulsion requires production and storage of antimatter at levels orders of magnitude beyond current capability. Relativistic flight requires energy sources and propulsion systems that do not exist. Suspended animation requires biological achievements that are not currently achievable. This does not mean these things will never be achieved. Science and technology have repeatedly achieved things that seemed impossibly distant when the effort to achieve them began. Nuclear energy was achieved within decades of the theoretical framework that made it possible. Computing power has followed an exponential growth curve for 70 years. Biotechnology has transformed medicine in ways that would have seemed miraculous to the scientists of a century ago. There is no reason in principle why propulsion physics, biological preservation, and related fields cannot advance dramatically over the next few centuries. But dramatic advance over centuries is different from foreseeable near-term capability. The interstellar travel problem is on the centuries to millennia timescale for any realistic technological development path. The crossing of 1 light-year by a human crew is a genuinely long-term challenge. Not forever out of reach, not achievable within any current institution's planning horizon. Let us talk about what the specific numbers we have calculated mean for our understanding of what human civilization would need to look like in order to seriously pursue interstellar travel. The smallest possible interstellar mission, a gram-scale probe at 20% of light speed, requires a 100 gigawatt laser array. Current global energy production is approximately 500,000 terawatt-hours per year, approximately 57 terawatts averaged continuously. The laser array for Breakthrough Starshot would consume approximately 0.2% of current global energy production during its firing sequence. This is achievable in principle with current global energy production if the necessary infrastructure were built, though the infrastructure itself represents an investment comparable to major national infrastructure projects. Scaling from gram-scale probes to kilogram-scale probes, with the possibility of more sophisticated instrumentation, scales the required laser power by a factor of 1,000. Scaling to ton-scale probes, with any possibility of sample return capability or more complex mission profiles, scales it by another factor of 1,000,000. Scaling to anything that might eventually support a human crew, which requires many tons of life support, food, habitat, and propulsion, scales the required laser energy by a factor that makes any laser propulsion approach economically impossible with any foreseeable global energy production level. Fusion propulsion, at a level sufficient to accelerate a crewed spacecraft to 10% of light speed for a 1 light-year crossing in approximately 10 years, requires energy of approximately 10 to the 23 joules, roughly 200 times current global annual energy production. Even if fusion technology were developed and global energy production were dramatically expanded, dedicating hundreds of times current global annual energy production to a single mission is not economically realistic for a civilization at any near-term technological level. Antimatter propulsion at a level sufficient for a crewed mission to cross 1 light-year in 5 years at high velocity requires perhaps 10 to the 22 joules of antimatter, roughly 20 times current global annual energy production, and requiring production of several kilograms of antimatter at 100% conversion efficiency, which itself requires many times more input energy than the antimatter would contain. What these numbers reveal is that serious human interstellar travel is not just a matter of better technology in the way that building a better airplane is a matter of better technology. It requires a fundamentally different energy civilization, one in which humanity's total energy production is many times larger than today's, in which exotic materials and propulsion systems that do not currently exist have been developed and scaled up, and in which the resources devoted to a single interstellar mission exceed the current GDP of large nations. This energy civilization is not impossible. A civilization that has colonized the inner solar system and developed the asteroid belt would have access to resources and energy from solar power at different distances, from the fusion fuel in gas giant atmospheres, from the material resources of asteroids and moons that dwarf what is available from a single planet. A truly spacefaring solar system civilization would have the energy and material budget to attempt interstellar missions in ways that are literally unimaginable from a purely Earth-based perspective. But the steps from here to a solar system civilization, and from there to interstellar capability, are each vast. The step from Earth to Mars, to the asteroid belt, to a full solar system civilization involves challenges that are already as daunting as anything humanity has attempted. The further step from solar system civilization to interstellar capability involves challenges of a different order of magnitude again. These are not steps that happen in decades or centuries. They are generational projects, not in the sense of 2 or 3 generations, but in the sense of many generations, stretching over centuries to millennia. Understanding this timescale is important, not because it is discouraging, but because it is honest. The honest understanding of the interstellar problem tells us that the relevant decisions are not being made today or in the next decade. They are being made over many decades by many generations of scientists, engineers, policymakers, and ordinary citizens who allocate resources toward or away from the technologies that will eventually determine whether interstellar travel becomes possible. The investment in fusion research, the investment in advanced propulsion physics, the investment in the space infrastructure that would eventually support interstellar development, these investments are being made or not made now, and their consequences will play out across centuries. This is a strange position to be in, making decisions whose consequences operate on timescales longer than any institution currently exists and longer than any individual can observe. The institutions that will develop interstellar travel do not yet exist. The people who will achieve it are not yet born. The science that will make it possible is not yet done. What exists now is the beginning, the foundational science, the early technology demonstrations, the philosophical and cultural framework that will either prioritize interstellar capability or not across many generations of incremental decision-making. The question of how long it would take humanity to cross 1 light-year is therefore not just a technical question with a calculated answer. It is a question about what kind of civilization humanity chooses to become over centuries and millennia. The answer depends not just on physics, but on whether the investment in the physics, the engineering, and the infrastructure is sustained across a time frame that no individual or institution can fully encompass. At the low end, current technology, the answer is 17,000 years. At the high end of what physics permits, near light-speed travel, the answer is a little over a year in objective time, or potentially days in subjective time. In between lie technologies that could be developed in centuries to millennia if the civilizational commitment to developing them is sustained across those timescales. What determines which of these answers is the relevant one for humanity is not physics. Physics is fixed. What determines it is everything else: will, investment, institutional continuity, scientific progress, the choices made by many generations of people who each have access to only a small part of the problem and who each contribute only incrementally to the solution. Whether those incremental contributions accumulate into genuine interstellar capability depends on whether the civilizational project is maintained across timescales that individual humans cannot directly observe. This is the actual answer to the question of how long it would take humanity to cross 1 light-year. It depends on what humanity does, on choices that are being made now and will continue to be made by people not yet born. The physics gives us the range. The civilization determines where within that range the answer ultimately falls. Right now we're at the bottom of the range, with what we have, with what we have built, with the technology that is actually deployed in the actual universe. 17,000 years. That is where we are. Where we end up depends on everything that happens between now and whenever the crossing actually occurs. And that is genuinely unknown. Not because the physics is unknown, the physics is clear, but because the choices of many generations across many centuries are not yet made and cannot be predicted from where we stand today. The light year waits. It has been waiting for 4.6 billion years since our solar system formed. It will continue to wait. The question is whether humanity, across whatever timescale it takes, will close the distance between where it is and where the universe is, or whether the universe will remain as it is now, mostly unreachable, present everywhere to our observation, available nowhere to our presence. Begin with the departure. A spacecraft leaving our solar system headed toward interstellar space would first have to escape the Sun's gravitational influence. The boundary of the solar system in the gravitational sense, the heliopause, where the solar wind meets the interstellar medium, is at approximately 120 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, 150 million kilometers. The heliopause is therefore approximately 18 billion kilometers from the Sun. Voyager 1 crossed the heliopause in 2012, after 35 years of travel at approximately 17 kilometers per second. An interstellar spacecraft at Daedalus level velocities, 12% of light speed, would cross the heliopause in approximately 4 hours after launch. The solar system would shrink behind it at a rate that seems rapid relative to Voyager's glacial pace, but that still takes hours to produce visible change in the appearance of the Sun. At departure from Earth orbit, the Sun is a dazzling disk. By the time the heliopause is crossed, 4 hours of travel at 12% light speed later, the Sun has shrunk to a brilliantly bright star, but still clearly distinguishable from all other stars by its intensity. Earth is no longer resolvable as a disk. It has become a point of light, invisible against the glare of the Sun. Then the long transit begins. 1 light-year of space. At 12% of light speed, this takes approximately 8.3 years. The spacecraft is alone in the space between stars. Not in the absolute physical sense, because the interstellar medium contains gas and dust and cosmic rays and the faint photons of the cosmic microwave background, but functionally alone. No planets, no objects of any kind within any practical distance. The darkness in every direction, broken only by the stars, which look essentially the same as they do from Earth, because the baseline change in position over 8 years of travel is sufficient to produce visible stellar parallax, the apparent shift in nearby star positions relative to the distant background, but not sufficient to dramatically change the overall appearance of the sky. The stars ahead would be slightly blue-shifted toward shorter, bluer wavelengths by the Doppler effect of the spacecraft's velocity. At 12% of light speed, the blue shift factor is approximately 1.06, a 6% shift in wavelength. This is perceptible to instruments sensitive to color, but would be barely noticeable to the human eye. The stars would look very slightly bluer in the direction of travel, and very slightly redder in the direction behind. At 12% of light speed, the relativistic aberration, the apparent compression of the star field toward the direction of travel, would be small but measurable. The sky would look essentially normal to human perception. At higher velocities, the effects become more dramatic. At 50% of light speed, the Doppler blue shift factor is approximately 1.73, a 73% shift. Stars in the direction of travel would appear significantly bluer. Some ultraviolet stars would shift into visible range, making them brighter. Some infrared stars would shift into visible range. The star field would begin to appear compressed toward the direction of travel through relativistic aberration. The sky would look noticeably different from what you see from Earth. At 90% of light speed, the sky would be dramatically transformed. The Doppler factor is approximately 4.4. Stars in the direction of travel are shifted far into the blue and ultraviolet. Many would become invisible because their emission is shifted entirely out of the visible range into X-rays. The aberration effect would concentrate most of the visible stars into a bright ring ahead of the spacecraft. Looking forward, you would see a concentrated bright disk of shifted starlight. Looking behind you would see relative darkness, the backward shifted stars dimmed and reddened, most below the threshold of visibility. At 99% of light speed, the forward disk of concentrated starlight would be brilliant and compact. The entire sky's worth of stars would appear concentrated into a small, bright circle ahead. Behind would be near absolute darkness. The cosmic microwave background, normally a faint, uniform glow at 2.7 Kelvin, completely invisible to human eyes, would be blue shifted in the direction of travel into infrared and eventually visible wavelengths, contributing to the brightness of the forward disk. These are not speculative embellishments. They are the direct mathematical consequences of special relativity applied to the propagation of light. A camera aboard a relativistic spacecraft would record exactly these effects. The universe genuinely looks different from inside a fast-moving spacecraft in ways that have been calculated precisely and that could, in principle, be photographed and transmitted back to Earth. The experience of time during the transit is the strangest element of all. Strange because it is simultaneously mundane and profound. For the crew aboard the spacecraft, time passes normally. They age, they sleep, they work. They experience the full texture of days and weeks and months, as they always have. The time dilation is not felt from the inside. You do not experience your clock running slow relative to Earth. You simply experience time. At 12% of light speed, the time dilation is small, approximately 0.7%, meaning that the crew experiences approximately 0.7% less time than Earth clocks measure. For an 8.3-year transit, this amounts to about 3 weeks. Not significant. At 90% of light speed, the time dilation factor is approximately 2.3. The crew ages at less than half the rate of Earth clocks. For a transit of approximately 1.1 years of Earth time, 1 light year at 90% light speed, the crew experiences approximately 6 months. 6 months of normal life aboard a spacecraft, conducting experiments, maintaining systems, living ordinary daily lives, while more than a year passes on Earth. At 99% of light speed, the crew experiences approximately 7 times less time than Earth clocks measure. 1 light-year crossed in slightly more than 1 year of Earth time, while only approximately 7 weeks pass on board. 7 weeks, a period shorter than a typical Antarctic expedition, to cross the first light year from our solar system toward the nearest star. The paradoxical quality of this is that the crew would feel no different than if they were not moving relativistically at all. Their internal experience of time is normal. Their clocks run at the rate they always run. Their biological processes proceed at their normal pace. They eat, sleep, age, think at the rates they always have. The time dilation is a relationship between their reference frame and Earth's reference frame, not a property of their experience from the inside. But when they arrive, if they turn around and return to Earth, they will have aged less than the people on Earth have aged. This is not a thought experiment, it is a confirmed physical consequence of special relativity. The twin paradox, the thought experiment in which one twin travels at relativistic speed and returns younger than the Earth-bound twin, is not a paradox at all. It is a straightforward prediction of special relativity that has been confirmed repeatedly through experiments with subatomic particles. Muons, produced by cosmic ray interactions at the top of the atmosphere, survive to reach the surface only because their time dilation at relativistic speeds extends their effective lifetime. Atomic clocks on airplanes and satellites show the predicted time dilation. The effect is real. This means that relativistic interstellar travel, if achieved, would permanently alter the relationship of the travelers to Earth in a way that has no precedent in human experience. Travelers who cross 1 light-year at 99% of light speed and return would have aged approximately 14 weeks. More than a year would have passed on Earth. People they knew would be more than a year older. Events would have occurred that they missed. The faster the travel, the larger this gap. A round trip to Alpha Centauri at 99% of light speed, 4.24 light-years each way, would take approximately 4.3 years of Earth time per leg. The crew would age approximately 4.3 divided by 7, about 7.5 months per leg. A round trip of approximately 8.5 years of Earth time would age the crew by only about 15 months. Meanwhile, on Earth, 8.5 years would have passed. Children would be 8.5 years older. Parents who were alive at departure might be dead at return. Cultural and political changes would have accumulated over 8.5 years. The traveller returns to a world that has moved on without them, not dramatically, but measurably. The faster the travel speed, the more extreme this disconnection. At 99.99% of light speed, the disconnection becomes so large that interstellar travellers become genuinely separated in time from the civilization that sent them, returning to a world that has aged by decades while they aged by months. This temporal disconnection is one of the most profound social and psychological consequences of relativistic travel, and it has received almost no serious analytical attention in the context of discussions about future interstellar missions. The astronaut who returns from a relativistic interstellar journey has experienced something that no one on Earth has experienced, and that no one on Earth can share. The 15 months of shipboard experience aboard the Alpha Centauri voyage correspond to 8.5 years of Earth history that they did not participate in. They are simultaneously contemporaries of the people they knew and displaced from them in time in a way that is not emotionally reducible to the 7 years of different experiences that two people on Earth might accumulate. The sociological implications for a civilization regularly conducting relativistic interstellar travel, if that ever becomes possible, are genuinely interesting. The development of a community of interstellar travelers who are progressively displaced in time from Earth-based society raises questions about identity, community, legal status, inheritance, relationships, and the meaning of membership in a civilization that the travelers are repeatedly out of step with. These are not science fiction questions. They are direct consequences of the physics that becomes relevant if relativistic travel is achieved. Let us now talk about what the psychological experience of existing in the crossing, of being a human being in the middle of an 8-year relativistic transit or a 70-year non-relativistic transit, would actually be like at the level of daily existence. The ISS provides our best empirical data on what it is like to live in a spacecraft for extended periods, and it is sobering in ways that the interstellar travel conversation usually does not acknowledge. ISS astronauts on 6-month missions consistently report the psychological challenge of confinement, of living and working in a space that they cannot leave, with colleagues they did not fully choose, under conditions that are simultaneously demanding and monotonous. The work is meaningful, and they know it is meaningful, but the meaning of the work does not eliminate the psychological cost of the physical and social conditions. An interstellar spacecraft on a years-long or decades-long crossing presents the same challenges in amplified form. The confinement is more absolute. There is truly nowhere to go outside the spacecraft. The social group is more permanent. You cannot change who you are with at any point during the crossing. The return home, even for relativistic travel, is years to decades away. The cosmic environment outside the window is more uniform. Deep interstellar space offers nothing to look at that changes on any human timescale. The stars do not move perceptibly. The blackness is absolute in directions other than toward the concentrated star fields of the galactic plane. For month after month, year after year, the view from the window is essentially unchanged. This environmental monotony, combined with the social intensity of a small closed group, is perhaps the most reliably documented source of psychological distress in long-duration isolation environments. The brain is a system that evolved in environments of high variability: changing weather, changing landscape, changing social group, changing seasons, changing food sources. Depriving it of this variability produces reliable deterioration in mood, motivation, and cognitive function, even when the individual is otherwise healthy and the mission is meaningful. What does this mean for interstellar travel? It means that the psychological design of an interstellar spacecraft is as critical as the propulsion design. The social architecture, the physical architecture, the planned activities and unplanned freedoms, the communication with Earth and the acknowledgement of its increasing delay, the cultural and artistic life of the crew, the governance system, the medical support. All of these need to be designed with the specific psychological demands of years to decades of deep space transit in mind. This design work has barely been started for long-duration solar system missions. For interstellar missions, it has not begun. The communication delay problem deserves special attention in the context of psychological support. During a 1 light-year crossing at 12% of light speed, Earth is receding at 0.12 light-years per year. The communication delay, the time light takes to travel the growing distance, starts at essentially zero and grows to 1 light year, 1 year each way, by the end of the crossing. A crew member who experiences a personal crisis at the midpoint of the crossing is approximately 6 months of light travel time from Earth. Their message takes 6 months to arrive. Earth's response takes another 6 months to return. The communication round trip takes more than a year. This delay does not just make crisis intervention difficult, it makes all communication fundamentally asynchronous in ways that change its psychological character. Real-time emotional connection, the kind that sustains people through difficulty, is impossible. What replaces it is a different kind of connection: pre-recorded messages, asynchronous exchanges where questions and answers are separated by months or years. The cultivation of a different relationship to Earth-based community that acknowledges the communication delay as a permanent feature of reality rather than a temporary inconvenience. The psychological adaptation required for this, the development of an inner life that can sustain itself with significantly less external connection than humans are evolved to require, is not a well-studied capability. Some individuals have it, people who thrive in long-term isolation, who have rich inner lives, who can maintain motivation and emotional stability without external feedback. Most people do not have it at the level required for years-long interstellar transit. Identifying and selecting for this capability and developing training and support systems that build it in crew members who have it in potential form is a critical gap in current interstellar mission planning. A gap that is made more critical by the fact that it has not been recognized as such. Let us talk about what children might experience if born on an interstellar spacecraft. The generation ship scenario, in which the people who arrive at the destination are descendants of the people who departed. A child born during an interstellar crossing has no experience of any planet, no experience of changing weather, of seasons, of landscapes that extend beyond what can be seen from a single viewpoint, of populations larger than a few thousand, of institutions that extend beyond the spacecraft's own internal governance. Their entire world is the ship. This is their home in the absolute sense, not just where they live, but the totality of their physical experience. The developmental consequences of growing up in this environment are genuinely unknown. The developmental psychology of children in normal environments is reasonably well understood. The developmental psychology of children in environments as constrained and unusual as a generation ship is not. There is no analogue from which to extrapolate. Antarctic research stations are inhabited for months, not lifetimes. Submarines are deployed for months. Remote communities have exposure to the broader world through technology and occasional travel. No environment in human history approximates the generation ship in its combination of physical constraint, social closure, and indefinite duration. What we can say is that children are plastic in ways that adults are not. They adapt to their environments during development more thoroughly than adults adapt to changed environments. Children who grow up on a spacecraft would develop their sense of normal based on that spacecraft. The rolling hills and open sky and complex weather systems and social diversity of Earth would be as foreign to them as any alien environment. They would know about it from records and education, but they would not have it as embodied experience. Whether a child who grows up on a spacecraft is disadvantaged by not having Earth experience depends entirely on what they are being prepared for. If the spacecraft is their permanent world, if they will live their entire life in transit between one star and another, and die before arrival, then the spacecraft is a complete environment, and the lack of planetary experience is not a deprivation. If they are expected to arrive at a destination and settle a new world, then the lack of experience with a planetary surface is a genuine deficit that would require addressed through simulation, training, and the difficult experiential learning of encountering a real planetary environment for the first time as an adult. The cultural life of a generation ship, the art, the music, the religion, the philosophy, the narrative traditions that give meaning to a community, would develop in response to the specific conditions of life in transit. Over generations, this culture would become genuinely distinct from the Earth cultures that founded the ship. The children, growing up in the third or fourth or fifth generation of the crossing, would have a culture that their great-grandparents who departed Earth would not fully recognize, adapted to space, shaped by the specific social and physical conditions of a closed system in transit, carrying memories of Earth that are increasingly mediated through oral tradition and recorded media, rather than through any living person's direct experience. This cultural evolution is not a problem to be solved. It is an inevitable consequence of genuine settlement, of human communities adapting to the specific conditions of the environments they inhabit. Every human culture on Earth has evolved in response to specific environmental and social conditions. The generation ship culture would do the same. What makes it different is the rate of isolation, cut off from Earth culture almost completely by the communication delay and the physical separation, and the specific conditions of the adaptation, the closed space, the fixed social group, the uniform environment, the indefinite transit. Whether the culture that arrives at the destination bears enough continuity with the one that departed to be considered the same civilization, whether the mission's purpose, as understood by the founders, has been transmitted meaningfully through generations to the people who will fulfill it, is genuinely uncertain. History offers examples of communities maintaining mission coherence across many generations. It also offers examples of the original mission being reinterpreted, forgotten, or transformed beyond recognition as the founding context recedes. Which of these fates a generation ship culture would experience cannot be predicted in advance, and can only be managed by attending carefully to the institutional and cultural mechanisms for transmitting purpose across generations, mechanisms that are not currently well understood even for terrestrial communities. Let us now bring all of these threads together: the physics of crossing times, the psychology of transit, the culture of generation ships, the civilizational investment required, and ask what the picture as a whole reveals about our actual situation. Our actual situation is this: we are a young technological civilization, perhaps 10,000 years old in the agricultural sense, perhaps 300 years old in the industrial sense, perhaps 70 years old in the spacefaring sense, embedded in a galaxy that is 13.8 billion years old and 100,000 light-years across. The nearest star is 4.24 light-years away, a distance that our fastest technology would take 17,500 years to cross. The physics permits much faster travel, but requires energy and engineering that are centuries to millennia away from being achievable with any foreseeable civilizational development path. We can observe everything. We can reach essentially nothing. We are surrounded by a universe that is simultaneously completely accessible to our observation and completely inaccessible to our physical presence. The light from 13 billion years ago reaches us continuously. The nearest star is beyond our reach for thousands of years. This is our situation. not a temporary situation that better technology will soon remedy, a structural situation, the consequence of specific facts about physics and biology and the current stage of civilizational development that will define humanity's relationship to the universe for centuries at minimum and possibly for millennia. The interstellar distances are not a problem that will be solved in the next generation. They are the conditions within which the next many generations will live. What does this mean for how we should think about ourselves and our place in the universe? It means that the universe visible to us, the 93 billion light-year sphere of the observable universe, is essentially all the universe we will ever have. Not because nothing exists beyond the observable horizon, but because nothing beyond it can ever reach us or be reached by us, even in principle. The observable universe is our universe, the entire context of our existence, and the entire scope of our potential knowledge about the cosmos. Within that universe, the Milky Way galaxy, our home galaxy, is the only region that is even potentially reachable on civilizational timescales. The 100,000 light-year diameter of the Milky Way can, in principle, be crossed by a civilization with fusion propulsion in approximately 500,000 years. A long time, but not longer than the timescale over which modern humans have existed. Our galaxy is the effective scope of potential human civilization on any timescale we can meaningfully contemplate. Within the Milky Way, the nearest few hundred light-years, the local stellar neighborhood, is the region potentially reachable within the timescale of a few thousand years, even with nuclear pulse propulsion. This neighborhood contains thousands of stellar systems, each potentially harboring planetary systems, some of which may have planets in habitable zones. This is the effective scope of interstellar exploration on the timescale of historical human civilization. The region within which probes could be sent and data received within a span of time comparable to recorded human history. And within that neighborhood, the nearest few dozen light-years, within approximately 10 light-years, is the region that could potentially be reached by crewed missions on timescales of centuries if fusion propulsion is developed. A civilization with fusion rockets could reach the dozen or so stellar systems within 10 light-years over the course of several centuries. These systems, including Alpha Centauri, Barnard's Star, Wolf 359, Lalande 21185, Sirius, and a handful of others, represent the nearest potentially reachable destinations for human expansion in any scenario that does not require physics beyond what we currently understand. 1 light-year, the distance we have been examining throughout this exploration, is less than a quarter of the distance to the nearest of these destinations. It is the opening step of an interstellar journey. It is the threshold of the true interstellar scale. And crossing it, as we have established, requires either tens of thousands of years with current technology, or decades to centuries with fusion propulsion technology that does not yet exist, or years with antimatter technology that is centuries to millennia away, or, potentially, less than a year in subjective time, with truly relativistic travel that requires energy civilization far beyond current capability. The question of how long humanity needs to cross 1 light-year does not have one answer. It has a spectrum of answers that depends on when you are asking, what civilizational investment has been made in the relevant technologies, and what definition of crossing you accept. Physical crossing by a human crew versus crossing by an unmanned probe versus crossing in objective time versus crossing in subjective time. What is constant is the scale of the challenge. The light year is genuinely far. The physics is genuinely hard. The engineering is genuinely demanding. The resources are genuinely beyond what our current civilization can mobilize for any single purpose. and the human biology and psychology that would need to survive the transit are genuinely fragile in ways that the physics does not care about. This is the truth of the interstellar problem. Not discouraging. Truth is not discouraging, it is clarifying. Not a reason to stop thinking about interstellar travel. On the contrary, understanding the true scale of the challenge is the prerequisite for addressing it with appropriate seriousness. But honest. As honest as the numbers require. As clear as the physics demands. 1 light-year, the opening measure of the interstellar scale. The distance that tells us where we actually are in the universe and what our relationship to the rest of it actually is. Vast, cold, mostly empty, barely accessible. And for that reason, for exactly that reason, all the more extraordinary as the context within which something as improbable as a civilization capable of asking these questions has managed to arise. There is a specific moment that happens when you let the numbers be real. Not when you read them. Reading them is easy. The brain processes the symbols and moves on. When you let them be real, when you actually try to inhabit the scale, when you take the 17,500 years that Voyager would need to cross 1 light-year and place it against the 5,000 years of recorded human history and feel what that ratio actually means. When you take the 9.46 trillion kilometers of 1 light-year and try to find any analogue in human experience for a number that large and find that there is none, that the number simply exceeds the range within which human intuition operates. That moment produces a specific kind of feeling, not quite awe, not quite fear, not quite despair, something quieter than any of those. A kind of stillness that comes from understanding your actual position rather than your imagined one. Your actual position is this. You are on a small rocky planet orbiting an unremarkable star. The nearest other star is 4.24 light-years away, a distance that would take the fastest spacecraft humanity has ever launched 73,000 years to reach, if it were aimed in that direction. The galaxy containing your star has approximately 200 to 400 billion other stars, distributed across a disk 100,000 light-years in diameter. The observable universe contains approximately 1 to 2 trillion galaxies, each containing hundreds of billions of stars. Almost all of this, essentially everything in the universe, is not just far away, but unreachable on any timescale that means anything to a civilization, let alone to a human life. You can see all of it. The light from every corner of the observable universe arrives continuously at your instruments. You can measure the temperature of the cosmic microwave background to 6 decimal places. You can determine the chemical composition of stellar atmospheres 10,000 light-years away through spectroscopy. You can detect gravitational waves from black hole mergers 1 billion light-years distant. The universe is completely transparent to observation in ways that make everything in it an open book if you have the instruments to read it. And you can reach essentially none of it. The farthest human-made object from Earth, Voyager 1, is approximately 0.0024 light-years away, less than 1/4% of 1 light-year. After 47 years of continuous travel at speeds that would have seemed impossible to any previous generation of humans, it is the most distant thing we have ever sent anywhere. It is a rounding error on the scale of the interstellar problem. This is the actual human relationship to the cosmos, observer and not traveller. Reader of a universe that we can see in its entirety but visit in a negligible fraction. inhabitants of one small system who have sent one small probe to the very beginning of the interstellar scale after half a century of effort, and who look out at everything beyond and know, if they are honest, that the everything beyond is not coming and cannot be reached in any human lifetime with any technology that exists or will exist in the foreseeable future. This sounds like a counsel of limitation. It is not. It is a counsel of accuracy. There is a difference between a universe that is inaccessible because physics forbids access and a universe that is inaccessible because we are early. We are early. The human species has been technologically capable of reaching beyond its home planet for approximately 70 years. In those 70 years, we have reached the Moon, sent probes to every planet in the solar system, sent 2 probes to interstellar space, and landed rovers on Mars. These are extraordinary achievements given the starting conditions. A species that 70 years ago had never been to space now has operational spacecraft in the interstellar medium. The trajectory of development is real. But the trajectory is also genuinely long. The gap between where we are and where we would need to be to cross 1 light-year in any meaningful time frame is not a gap that closes in decades, it closes in centuries to millennia. The fusion propulsion that could cross 1 light-year in years does not yet exist, and the technology to build it is not yet in hand. The antimatter propulsion that could cross it faster requires production and storage capabilities that are orders of magnitude beyond anything demonstrated. The relativistic travel that could collapse the subjective crossing time requires energy sources that are beyond any foreseeable civilizational development path. The honest answer to how long humanity needs to cross 1 light-year is therefore not a number. It is a conditional. If humanity develops fusion propulsion, genuinely develops it, builds it, deploys it at the scale required for interstellar missions, the crossing time falls to decades. If humanity develops antimatter propulsion on a trajectory that requires centuries of sustained scientific and engineering investment, it falls to years. If something more radical, something that requires physics we do not yet understand, is discovered and developed, the crossing time could collapse further. But none of these conditionals are guaranteed. None of them are imminent. All of them require a civilizational commitment to a project whose timescale exceeds any institution currently in existence. Whether humanity makes that commitment, whether the investment in the physics and the engineering and the social and institutional structures needed to pursue interstellar capability is sustained across centuries, depends on choices that are being made now and will continue to be made by people not yet born. The physics is fixed. The civilization is not. What determines where within the vast range of possible answers, from 17,500 years to perhaps a decade, the actual answer falls, is not the physics. It is the human project of building, sustaining, and directing a civilization capable of the scale of effort the crossing requires. This is simultaneously humbling and empowering. Humbling because the scale of what is required is so much larger than anything our current civilization has attempted. Empowering because the physics does not forbid it. The universe is not locked against us. The crossing is possible. Physics says so. The question is whether we can become the kind of civilization that is capable of achieving what physics permits. We are 1 light-year from the beginning of the interstellar scale, 9.46 trillion kilometers from the starting line of a journey that extends to 4.24 light-years to the nearest star. 100,000 light-years to the far edge of our galaxy, 2.5 million light-years to the nearest large galaxy, billions of light-years in every direction to the edges of what we can observe. We can see all of it. We are at the beginning of reaching any of it. The distance between those two facts, between what we can observe and what we can reach, is where we actually live. In the gap between the universe we can know and the universe we can go to. In the light of everything that is real and distant and beautiful and almost entirely beyond us for now. For now. That qualifier matters. We are early. The universe is not going anywhere. The physics does not change. The light years will remain exactly what they are while civilization develops over centuries and millennia toward whatever it becomes. Whether that development produces interstellar capability, whether the conditional is eventually satisfied, is genuinely unknown. But the development is happening. In every fusion reactor that brings controlled nuclear fusion a step closer, in every advanced propulsion study that characterizes what is required, in every telescope that maps the nearby stellar neighborhood and identifies where the destinations would be, in every spacecraft that pushes the boundary of what we have demonstrated, in every generation of scientists and engineers who contribute their work to a project that is larger than any of them individually, and that they will not individually see completed. This is what it looks like to be at the beginning of something genuinely enormous. Not the dramatic beginning of a story that resolves quickly. The quiet, sustained, intergenerational beginning of a project whose timeline is centuries, and whose completion, if it comes, will be achieved by people who are not yet born, using knowledge that is not yet discovered, with capabilities that do not yet exist. 1 light-year, where the interstellar scale begins, where the familiar universe ends and the cosmos starts, where our observation reaches everywhere and our physical presence reaches nowhere yet. The gap between those two things is the central fact of our situation. We live inside it. We look out from inside it at a universe that is simultaneously completely known to us in its large-scale properties and almost completely unreachable in its physical extent. We are here, in this solar system, on this planet, in this moment, and the light from everything else arrives continuously, as if to remind us that it is all real and all present, even if almost none of it is reachable. That is enough for now. The observation, the knowledge, the understanding of what is real and how far it is, and what it would take to reach it, and what the numbers actually mean when you let them be as large as they are. 1 light-year. The universe starts there. We have not crossed it yet. We know at least what crossing it would require, and knowing that, honestly, precisely, without the comfortable fictions, is where the journey actually begins.